Okay, today I want to talk to you about energy conservation. Our goal for today is to understand that energy is a quantity that in normal circumstances can be thought of as constant. You will see how for some types of problems, energy conservation makes solving the problem much easier than trying to analyze the situation using forces and motion equations. Okay, you want to watch this video of Trevor throwing the puck vertically, and there's 4 different regions you want to focus on. 1 is when he's positioning the puck. 2 is when he's adding energy, 3 is when it's rising, and 4 is when the puck is falling. Okay, when we graphed this out in LagerPro yesterday, we got a graph that looked like this. You can see in the first region that the energy, total energy, is pretty much constant as Trevor positions the puck. In the green region is where Trevor is doing work to the puck. He is adding energy. In the last 2 regions, it's important to see that the energy remains constant. The total energy should be a perfectly flat horizontal line. And as it's rising, it loses kinetic energy and gains potential. When it hits its highest point, the kinetic energy hits 0 and the potential energy becomes maximum. So the major idea is that there are many circumstances where total energy will be constant, such as when the puck leaves the stick and then returns back to the stick. The entire time it's in the air, energy is constant. Okay, we have this conversion of energy in this video of the guy shooting the hockey puck. You will see his elastic energy is going to turn into kinetic energy. We can see this in Cut the Rope, where elastic energy is going to turn into kinetic energy and then eventually turning into gravitational energy. That then returns back to kinetic energy. Okay, try it mathematically. So what we want to do is we want to find the speed of launch and the maximum height this spring will obtain. You might want to pause it at this moment and see what you can do. Okay, the spring has a mass of 10 grams, a spring constant of 600 newtons per meter. The spring was originally 5 centimeters long, but we compressed it to 2. So find the elastic energy stored in the spring, and then use that to find the launch speed, and then use it again to find maximum height. Okay, you can see what we want to do here is set total energy equal to total energy. We start with elastic, we end with gravitational potential. This is to find the maximum height. You plug in the values and solve for height. To find the speed of launch, you do again total energy equals total energy. You start with elastic, you end with kinetic. You plug in your values and you solve for the speed. Okay, we saw this in lab when we were firing Trevor across the ice. We gave Trevor a certain amount of elastic energy. The farther back we pulled it, the more elastic energy he was going to have. We then fired him across the ice, and that elastic energy turns into kinetic energy. So if you wanted to find his speed mathematically, you set the elastic energy equal to kinetic energy and solve for speed. Okay, we have this other example that you could try on your own, where we have a 600-gram apple that we place in a slingshot. We pull the slingshot back 1.2 meters. The spring constant of the system is 300 newtons per meter, and you want to find the speed of the apple when it leaves the slingshot. Okay, so we got elastic energy turning into kinetic energy. Use the conservation of energy to find the speed of the apple. The final one I'd like you to try is using the idea of energy conservation to find the speed of a roller coaster car at 2 different locations. Assume the car is nearly at rest at point A and find the speed at points B and C. Start by asking yourself what kind of energy it possesses at each of these points, and then set the energy at the point you know, point A, equal to the energy at point B, and then, separately, the energy at point C. So if you'd like, you could pause and try and solve it. And it should look something like this. Total energy at A equals total energy at B. At B, it's only kinetic because the car is pretty much at ground level. And you solve for the speed at point B using the height at point A. At point C, you'll notice that it is above the ground and it is moving, so it's got both potential and kinetic. So you set the potential at point A equal to the potential and kinetic at point C, solving for the velocity at point C. So the big idea for today is energy equals energy, and you use it to find unknown values.